kids' lunches. That way I could put a little note in there to or make
Yeah, put little notes. Yeah, put little notes.
All right, here we go. I went ahead and did this one. So I don't know what you came up with as you were messing around with it. But my dash line here is the original. That's your E to the X curve. So the purple line, I did the upside downness. And then the pink line, I doubled the vertical. And then the final black line, I lowered it down one. How does that look to everybody? Just generally speaking. Oliver?
Is the asymptotes on the last one the same?
The asymptote actually, I should have added that in, Oliver. The asymptote is actually down here.
Okay.
Because the whole shebang got dropped down, including the asymptote. Yeah.
Okay.
How come the other one didn't do the same thing for the +2? For the one right
Oh,
before.
it should have. It should have.
should have?
Yep, it absolutely should have. So I think I erased that one, but thank you. I was rushing through trying to get done before lunch. And I think I messed that up. So it was E to the X +2 on the end. So we knew, okay, here's the original. We knew it was going up 2. And that asymptote, everything went up 2. So the original asymptote was at 0, it went up to 2. The original intercept was at 1, it went up to 3. Yes, very good, thank you, Sabrina. Yep.
So the asymptote on the on C would it be 0
On which one?
on C?
No, the whole thing, the entire picture gets dropped down 1. So the original asymptote of every exponential is at 0,
Yeah.
right? This one got turned upside down and stretched. That didn't change the asymptote. But when you lowered the picture, that changes the asymptote. So the asymptote is now down here. Because the whole picture gets dropped down 1.
Right. But if it got, oh, never mind.
All right, so yes, thank you, Sabrina. Perfect. All right, now we're going to talk a little bit about the logistic function. That's another one of our BFFs. Do you remember what that one looks like? The logistic function.
It had 2 asymptotes and it went like this.
It had, no, it wasn't a step function. No, it wasn't a step function. It had an asymptote here and an asymptote here. And then it kind of squiggled in between those 2 asymptotes like that. So when we're going to be sketching some, these are, number 7 there, those are examples of logistic equations. When we sketch them, we're going to be interested in that point and in where these 2 asymptotes are. That's what we're going to be interested in. So let's look at the first equation and figure out what's going on. Now, if I'm not using a calculator, I'm not real excited about graphing this thing. I mean, this is going to be some weird stuff. But let's talk about if we can figure out this point in these asymptotes, then we can just fill in that shape, right? So we just need to figure that out. Lucy?
Is the B value always going to be less than 1?
The B, well, it doesn't have to be, but if it's going to be a logistic growth function, it does. Okay, these things can go up and they can also come down, and that B is going to control that.
Okay.
But if we're going to do growth function, yeah. Okay, all right, so let's take a look at what we know we can find. Can we find a y-intercept? That's what this point is right here, it's a y-intercept. How do we find the y-intercept?
Plug in
Let x be 0, right? Let x be 0. It doesn't matter if it's linear, quadratic, logistic, let x be 0. So if x is 0, what do we have here? If x is 0, this would be 1 times 3 plus 1, 8 divided by, so we're going to have y-intercept at 2. Everybody okay with that? Now, these asymptotes are really like containing the picture. So if we were gonna describe this end behavior out here, let's say this asymptote was y=6. Then the end behavior of this picture would be that we are approaching 6 from the bottom. Would you agree?
Yeah.
So if the asymptotes are kind of describing the end behavior, we need to look at what happens to this as x gets really, really big. So what happens to this right here as x gets really, really big?
It gets smaller.
It gets smaller, right? And eventually it gets so small that we'll think of it as 0. It'll disappear eventually. And if that's 0, then timesing it by 3 is still gonna be 0. Adding it to 1 will be 1, so we have 8 over 1. So that top asymptote is up here at 8.
I'm confused, what is the right equation that you're going, or did you just draw that from that?
What are you talking
To
about?
the right, with the y=6.
Oh, I just made that up, so that we would figure out, how to find where that asymptote is. So we're finding the asymptote because it's the end behavior. So this asymptote is gonna be the end behavior as x goes that way. So what happens as x gets, think about this, it's getting really big negative. It's getting to be like the -100th power. What happens to 7/10
It's really big.
when you raise it to like the -100th power?
It's huge.
It gets huge. It gets huge. This is going to get ginormous. And when you times it by 3 and add 1, it's even gonna get more ginormouser. 8 divided by ginormouser is 0, really small. So that asymptote is going to be at 0. So our curve looks like that. Your asymptotes in a logistic function are the end behaviors. So to find end behaviors, you simply figure out what happens as x gets really, really big and really, really small. All right, here we go. Let's find our y-intercept. Here's our y-intercept. Oh, by the way, these guys, I know when we draw them, it's kind of hard to tell, but there's no symmetry about the y-axis here. You understand that, right? Yeah, it's not symmetric about the y-axis. Okay, here we go. What's my y-intercept gonna be this time?
20.
10, 2.
Okay, how do we find the y, where did I say y-asymptote? I meant y-intercept. How do we find a y-intercept?
Plug in 0.
Set x to 0. So what happens if I let x be 0? 1 times 2 plus 1.
Wait, why?
6 and 2/3.
So don't I get 20 over 3?
Is that
20 over
because-
3, my y-intercept?
Is that because like e to the power of 0 would be 1?
Mm-hmm. Anything to the power of 0 is 1. All right, now, let's ask ourselves what happens as X gets really, really big. Okay,
It makes it,
so as X gets really, really big, this would be like E, we're going out this way, so it's like to the negative 100. What's E to the negative 100?
super small.
Really small. So this is like disappearing. So where's that asymptote? 1. And if we let X get really, really small, then it's like E to the 100th,
That's very big.
which would be huge. And would make 20 over huge, which is 0. Now, I don't know if Lucy noticed this or not. And I don't know if any of you were listening when Lucy was asking a question. But Lucy said, will B, this is B, will B, the base, will B always be less than 1? And I said, yep, if we're growing, if it's a growth. Well, wait, that's a growth picture, and B is not less than 1,
Well, it's 1 over.
but it's to the negative power. So this is actually 1 over E to the X, isn't it? So it's just exactly like this equation. It looked a little different, but it is. A couple of you have already noticed something. You've already noticed that that top asymptote is at this number. That number is called the limit to growth. And that vocabulary makes perfectly good sense to you because that is the limit to the growing, right? It's not gonna go past that. I do wanna caution you, that will only be the case if that number is a 1. If that number is not a 1, if you think about it, let's say this had been a 2. As X gets really, really big, this gets small, so you have 8 over 2. Now your asymptote would be at 4. So maybe a better way to think about it is to think about it like this. That's gonna be your top asymptote. In a growth, in a logistic growth problem.
Will that like always in these situations, like be a way to find your top asymptote? Like if it was like 20 over 4 plus 2 to the negative X, your asymptote, your top asymptote would be 5?
Yep.
So you assume that the lower bound is going to be y equals 0?
Yep.
Okay.
Yep. I'm trying to think what we have to do. We have to probably add or subtract something on the end of the equation to change that.
Oh, okay.
Because since the numerator has no variables, it's staying constant, but the denominator is gonna get huge.
Yeah.
It's always gonna go to 0. Yep.
Okay.
All right, here we go. We've got a couple of word problems to do. Using the data in 3.5, right here, the population of San Jose, California, and assuming the growth is exponential, when will the population of San Jose surpass 1 million persons? The other day, we wrote some exponential equations. Remember, this is your format? And the key to being able to do that without using a sophisticated calculator computer deal, the key to being able to do that is to have one point with an x-coordinate of 0. In other words, to have the initial value, to have the y-intercept. Because remember what happens? If we put 0 in for x and 782,000 in for y, doesn't that give me a? Because this becomes 1 if I put 0 in here. Remember doing that the other day? So our equation, we can just start off with this. Now, to make that happen, I changed my points, and instead of using 1990 and 2000, I use 0 and 10. So what does that mean my X is going to stand for? X is not
Years
gonna be the
after
year,
1990?
X is gonna be how many years after 1990? We've done that before in other problems. Here you really need to, because trying to write an exponential with things, other numbers here is gonna be tougher to do. All right, so then what do we do next? Well,
Plug in a point.
now we gotta plug in the other point, right? So 895,193 equals 782,248. B to the 10th? Everybody still on board? Now, how do we solve that? I need to figure out what B is. So what do I need to do first?
Isolate B.
So 895,193 divided by 782,248 equals B to the 10th? Okay, then what?
10th root.
Either 10th root it, or I prefer personally, this is my preference, it doesn't matter, your calculator will do anything. I prefer to raise it to the 1/10 power. But that's the same as 10th rooting, right guys? And you can do either one on your calculator. So, 895,193 divided by 782,248 raised to 0.1 power. Did you get 1.01358? I rounded off at some point. Is that what you got? Somebody else, please, get that?
Yeah.
So what does that mean? That means my equation is y equals 782,248 times 1.01358 to the x. So that equation describes the data that they gave me. Now, the question is, when will the population surpass 1 million people? So what are some options I have?
Could you set y to equal to 1 million?
So I can go back to my equation and put 1 million here. Okay, that's one option. We're gonna do that. We're gonna solve that in a minute. But I wanna hear another option. What's another option, Finley?
Could you graph it and then they intersect with 1 million?
Exactly. So one equation would be 1 million. One equation would be this exponential. And somewhere out there, they're gonna cross, right? Oh, what?
We are confused on if this schedule's right. The one on Power School says that our period starts at 1:05.
Okay, I have no idea. Let me check. Mrs. Braun sent something out.
I think classes,
Okay, we go till, oh yes,
Sorry.
all right, we shall finish this next time, folks, sorry about that. I know the waiting is gonna be unbearable, but try to fight your way through it.